Maryam Aliakbarpour will be talking about estimation of entropy in constant space.
Thank you. So this is a joint work with Andrew McGregor, Jelani Nelson, and Eric Lingard. So let me start by introducing the general model of inference. We usually have a large data set that we see it as samples from some unknown distribution. Then we have our algorithm, which performs some inference task like testing, estimating, or learning, and it produces a result. Usually the question that we ask is how many samples do we need to perform this task up to a certain accuracy in error parameter. In many inference problems, when we solve the problem, we don't care about computational constraints such as memory or time that the algorithm consumes. However, in practical settings, especially when we are working with large data and big data, it's not practical to assume that memory and time are unbounded. So the algorithm has maybe time constraint and memory constraints. I think yesterday Guy's talk was about how adding time constraint would affect the sample complexity. Today, I mainly focus on memory constraint. Just to give you an example, suppose that you have a router which handles millions of packages per day. The size of any algorithm that you write for the router, the size of the memory of that algorithm is much, much smaller than the size of the data that it's working with. So this is like an example of a practical setting that you might think of algorithm with limited memory. Let me introduce the model that we're working in more formally. We have a unknown discrete distribution over 1 to n. We want to estimate some function of this distribution, mean, variance, pick your favorite function. And we want by receiving samples from this distribution, generate as an estimate f hat, such that the probability of error of f hat being larger than epsilon be bounded by delta. And for the purpose of this talk, we're focusing on the algorithms that they have limited memory. So there is a set of very relevant problems that have been considered in the literature. Our algorithm is basically in a special case of a streaming algorithm. But here we are focusing on properties of the underlying distribution. But in many other streaming algorithms, the focus is on estimating properties of the data stream itself, like the L2 norm or LP norm of the data rather than just the underlying distribution. So this is because that's a very famous model and many of you have potentially worked on it, I just want to highlight the differences. So we are in the setting 1 for the purpose of this talk. Many problems have been considered in this setting. This is just few examples of problems that with the flavor of, more towards learning theory and a statistical problem like parity learning, learning PDFs, learning concept class, distribution testing, and so on. This is by no means an exhaustive list, it's just a few examples. So let me define the question that we will consider in this talk. We're focusing on estimating entropy with memory constraint. The notion of entropy that we are considering is the most famous notion of entropy for TCS community, the Shannon's entropy. So we have a distribution which the probabilities are from P1 to Pn. And the definition of the entropy is basically sum of Pi log of 1 over Pi. For those of you who don't know what entropy is, it's basically a notion that measures the information, or I really like this word, surprise in a random variable. So if you have an unbiased bit, the entropy is equal to 1. And if it's always 1 bit or always 0 bit, the entropy is 0, for example. So in the problem that we focused on was basically we received the samples from the distribution, we output h of hat, which is an estimate for the entropy with additive error epsilon, but 90% of the time, and we use only O of 1 words of memory. If you don't have any memory constraint, this problem can be solved with roughly O of theta of n over epsilon many samples. And prior to our work with O of 1 words of memory, there is an algorithm that can solve this problem with n over epsilon cubed n over epsilon cubed samples. Sorry, first one was samples. This is also samples. This is the sample complexity. So it's n over epsilon cube words of memory. What we did was basically removing a factor of 1 over epsilon from the sample complexity. So regarding the closely related model that I just explained, in this model, if you want to estimate the empirical entropy, like meaning the entropy of the data set, you require omega 1 over epsilon squared bits of memory, which imply, like if you consider the work to be polylog of k and sorry, this should be n and 1 over epsilon, this means that there is no algorithm that can estimate the empirical entropy of a data set with O of 1 memory. So this is also indicating sort of distinction in these model. I'm sorry, this should be n, so it's a domain size. So let me present an algorithm that estimates entropy. Like it estimates entropy and does a lot of things, but basically there is no memory constraint, and I want to indicate why it would be hard to implement the exact same algorithm when we have constraints on memory. This is an algorithm by Valiant and Valiant, which basically what it does, it computes something that is called fingerprint. If you don't know what fingerprint is a set of the statistic that captures for every frequency I, it says how many element appears with frequency I. So here, for example, there is one element appear 3 times, which is 3. But you sort of forget the labels of the element and store these as statistic. And in their paper, they show how using fingerprints, you can come up with a histogram of a distribution that is likely to generate the fingerprint. And based on that histogram, you can come up with a distribution that is compatible, like very close to the original distribution, but without the labels of the elements. So if I just ignore the elements, I can learn the underlying distribution fast, which is very, very fine for the properties that don't depend on the labels of the elements, such as entropy estimation or support size estimation. But in the essence of this algorithm is counting this statistic that needs to remember the frequencies of the element. And this is very hard to implement when you have only one words of memory, because for each of them, you kind of need to remember if an element had appeared before and how many times it appears. So it's very difficult to maintain such a thing. So in O1 memory, we have to focus on very primitive actions such as counting and adding and very, very simple stuff. So let me present a simple version of our algorithm, and then we built on this to see how we get our result. So if you just write the definition of the entropy, you can see that it can be considered as the expected value of log of 1 over pi, where pi is the probability of the ith element. So we exactly estimate this quantity because we just want to estimate the expectation of a quantity. We just take a bunch of samples, compute log of 1 over pi, and take an average of that, and that would be an estimate for the entropy. So There is one particular step here that we estimate p hat of I. What we do is you can estimate it in many ways. Like you can draw a bunch of samples, see how many of them are I and how many of them are not I, and then based on that ratio, you can compute p hat of I. The way that we use it is using negative binomial distribution, which is for n elements I, when we want to estimate p hat of I, we draw samples until we see t copies of I. And we're going to name that the number of samples that we saw as xi. And if you just consider, we consider the number of observed samples divided by t as xi. And it is very simple to show that the expected of xi is 1 over p. So I can basically estimate 1 over pi using just xi. And then just took an average of log over 1 over p hats that we had. So there are two parameters in the algorithm that is basically the degree of freedom that we have. One of them is R, like how much we repeat this process to get an accurate estimate of the expectation. And also how large is T, which I will explain the effects of these parameters in a second. So if you write the error of the entropy, you can, so remember that H hat was our estimate. You can write the error of the entropy in terms of two terms, like how far H hat is from its expectation and how far its expectation is from the true value that we want to estimate. So the first term here is called the bias of the estimate, and the second one is called the error of estimation. So the parameter t that I just showed you implies, basically dictates the bias of our estimator. And if we have O of 1 over epsilon many copies of an element I, it will imply a bias of epsilon over 2. And for the second one, it's a simple Chernoff-bound type argument that since the variance of xi's are small, you can show that if R is O of log squared and divided by epsilon squared, you get the right estimation, like such that the error of the estimate is at most epsilon over 2. So if I just put all of these together, is basically I have R repetition, and then t times n is basically the expected number of samples that I need to draw to estimate one of those negative binomials. The total sample complexity would be this quantity. So what we are hoping to get is basically n over epsilon squared. So I have one factor of epsilon extra here, and also I need to remove this log n. So in order to do this, I have basically two jobs. The first one, removing the epsilon, it's very unlikely that I can remove it from this part. This is like a Chernoff type thing. It seems like very necessary to keep epsilon squared here. But I can remove a factor of epsilon from t, and that would be our goal. And for the second part, I'll explain how to get rid of this log n factors. So what we're gonna do is come up with an algorithm that in that t is O of polylog 1 over epsilon instead of 1 over epsilon, and then get rid of log n factors too. So this is like a more advanced version of our algorithm. So remember that we had this extra bias term. Oops. So we're going to define this. We're going to define this bias term as the difference of the actual entropy minus the difference of our estimator, and it will become this expected value of log of yi. And it just, if we define yi to be pi times xi, this is the exact value of the bias. So our goal is to estimate this bias and reduce it from our estimator to get an unbiased estimator. So in this way, we don't have to worry about the bias of the estimator. So to do this, we write the Taylor expansion of sorry, let me add one thing. The expected value of yi is just simply by definition is equal to 1. And so we write the Taylor expansion around y equal to 1 for the log of yi and just replace this term with the Taylor expansion of this term. So instead of estimating the sky, I'm going to estimate this one. So so we use a truncated version of this infinitely many terms of the Taylor expansion up to the first S terms. There are two, basically I will end up with a term that is proportional to yi minus 1 to ds plus 1, and then the rest of the term. First, note that these yi are basically a negative binomial random variables up to some constant, some fixed coefficient. So they're actually nicely concentrated, and you can analytically show that their centered norm are actually bounded. So this part is mostly analytical. I don't need to draw any sample. I just need their bounded. So that's fine. For the second part, these are centered random variable that can be computed from a negative binomial, so I can estimate the rest of the term. And if you just write this down in expectation, it would be, you can write it in terms of a polynomial of degree s of pi's. And it's not hard to see that if you draw k samples and see if all of them are equal to each other or not, the probability of that equality happens is proportional to the pi to the k. So I have a polynomial of degree s that I need to compute, and I can compute them just using the samples. So this is enough to making t just polylogarithmic in 1 over epsilon. So then in the next step, I talk about how to remove log n factors. The idea is using a bucketing algorithm. What we do is basically partition xi into L different interval. And for each of those interval, we compute the weight of that interval times the conditional log of xi in that interval. So the goal was to compute log of xi. So we just write it in terms, like with just total law of probability, you can write it in terms of the conditional log of xi. Let's call this first term as the weight of that interval, and then let's call this part as the conditional entropy. We can estimate q hat and estimate each of these terms separately, namely q hat and h hat, and put them together to get the estimate that we want. We just do a simple, to compute the error here, we do a simple replacement. For the very last bucket, I just replace it, and instead of estimating its weight independently, what I do is just to take its weight to be 1 minus the weight of the rest. Just because we know that the sum of the weights are 1, this is possible. And then this will give us a very nice difference. If you just write a very few steps, like this is very simple if you actually write it down. But what it gives you is that it tells you that you can write the error in terms of the error in the estimation of the weights and in the error of the estimation of the conditional entropies. And one thing to note is that the further the error, the h of L is basically the very last bucket that is sort of hard to compute. Or it's like for the elements that have very small probabilities, but for the larger probabilities, it's easier to compute this quantity. But since it's multiplied by a very large thing, I can actually I can come up, like the buckets that are easier to estimate their weight, they will be more important in the error terms. So for the ones that are sort of hard to estimate, their significance in the error term is sort of smaller. So I don't need to estimate them very accurately. And then this subtle difference allows me to have different R and different T's for different R's for different part of the algorithm. And it lets me to remove basically log n factors. So with this, we will sort of remove the log n factors, and this would imply to the result of n over epsilon squared. And we leave this question open to how to come up with n over, if you can come up with a lower bound of n over epsilon squared. And thank you.
Do we have questions? First.
Do you know any result about the lower bound side? Like
Sorry,
this?
could you?
Yeah, like that's open question about the lower bound. Do you know any like non-trivial lower bound for this?
So I think there's a discussion part in our paper that we even came up with an example of what we think should be the right distribution for the lower bound. We think if you have two families of distribution, which one of them basically you have to construct this in a probabilistic way. In one of them, you have roughly 1 minus epsilon over too many fraction of your elements that are totally biased, like the probability is like, sorry, let me back up a level. We come up with two sets of distribution, and they are on bunch of pairs, basically. So you have pairs, and in each pair, you can create some biases. So like some of them are uniform or some of them are biased. But you can, if you make some of them, like 1 plus epsilon of them biased, and make 1 minus epsilon of them unbiased, and you flip this, these two sets of distribution will have very different entropies. So any algorithm that can estimate entropy will need to distinguish to these two sets of distribution. But we believe that you need n over epsilon squared to sort of distinguish these two.
For what memory? For
constant many
maybe even
words.
Yeah.
And words mean polylog epsilon in n.
The third meeting, I'll be able to pick you back up and escort you to your fourth meeting.
Okay, perfect.
Just between the first and second to third.
Okay.
After this.
Thanks. Another question or? Thank you.
Oh, okay, no more questions. Oh, here. Sure.
Yeah, thanks for the nice talk. So I found that technique of, I guess, using your samples to estimate those terms of the Taylor series for the log really interesting. And I was wondering, because in this context, the log is very, I guess, specific to, because you need that for the entropy. But I was just wondering if you've thought about similar in spirit techniques could generalize to other problems, either in streaming setting or other settings, just kind of, using this trick for other gains elsewhere.
I don't have any specific example in my mind, but that's definitely, okay. So I think generally speaking, I think this is not new to this work, but generally speaking, there are many works that use this idea of estimating something with polynomials, like Chebyshev polynomials. We probably have seen this. Here we use Taylor because we don't really care about the degree, but if you want to be like optimal, you can estimate functions with polynomials that are easier to estimate. It has appeared in the literature before. It's very unique to us, but I cannot think of any specific example now that would benefit from the Taylor expansion, but assuming it would maybe.
Yeah, no, I think that really helps. Thank you.
questions?
Hey, so you were looking at this type of problem that you have a minimal memory and you want to optimize the sample complexity. Do you know what happens in the other regime? I want to have optimal sample complexity. How much can I reduce my memory?
I think the algorithm that I basically showed requires O of like the number of samples times log n to store everything, because you need to count frequencies. I don't know if it's optimal or not, but it would be interesting. And there is one paper that by Diakonikolas, Kane, Goliakis, and one more person that I don't remember, but called 2019, if you want to look at it, for testing uniformity. Like the problem that they consider is slightly different, testing uniformity with limited memory. And they actually come up with a trade-off between the number of samples you need and the amount of like the number of samples and memory bits. For us, it didn't give any new results. Like it would just reiterate the lower bound that we have for the unlimited memory, but you can actually see there are like curves that are almost tight for these set of problems.
So currently, is it correct that we don't know any algorithm in a small O of n space that achieves optimal sample complexity?
Sorry, say that again.
So the current like optimal sample complexity algorithm requires omega n space or even n log n bits. Do we know any algorithm that just uses a small O of n bits? I don't know, a square root.
I think the upper bound, I don't know, I don't think.
All right, thanks.
I have a question. Okay, so I was wondering if similar techniques could be used if you have two different distributions to estimate KL divergence or something like that.
Maybe, yes. So we haven't really thought about this, but it's interesting. Can you estimate KL divergence? I think it boils down to the question that when you write those calculations, like what accuracy of p hat you would need. And
so like, if it could be the case that like, if, P is equal to delta and Q is equal to delta over uncontrolled, and that's small enough that like it makes a huge difference in terms of L, of course you can't do it.
thank you.
Okay, so if there are no more questions, let's thank Maryam again for the great talk.